Greetings to everyone. So, I welcome you all to this lectures on thermochemical surface treatments. So, if we recap what we have covered in the last lectures. So, we have seen that in the gaseous nitriding, if you have a particular alloying elements in the steel which you are subjecting to the gaseous nitriding treatment, then depending on the character of this alloying element and its interaction with nitrogen, we can expect different types of the growth pattern of the nitride layer. So, which we have seen that for first how the iron nitride layers when they want to grow, how the presence of alloying elements would interfere with the growth of iron nitride layers. In that context, we have seen about if we have a easy nitride forming elements and a difficult nitride forming elements, how that would influence the morphologies. And after that, we have seen if we try to grow the austenite, that is iron nitrogen austenite on the sample surface and the presence of alloying elements, how they would modify the way the austenite wants to nucleate and grow. So, now we will look into in this lecture the details of only alloying element interaction within the ferrite matrix. That means, it is a purely ferritic state, that means the matrix remains the ferrite and only the alloying elements would try to interact with the nitrogen which is coming inwardly and then try to form the nitride layers. So, in this context, so we have seen that from this so called Lehrer diagram, depending on the temperature and the applied nitriding potential, if you look at the previous lectures, we can actually tune whether we are allowing other iron nitrogen phases to develop or not. So, in most of the the next lectures, we apply the nitriding condition such that we form only ferritic, it will remain in a ferritic state. Yeah. So, in that, for example, if we take a iron chromium, so what is shown in this slide is it is a binary iron 7-weight% chromium alloy. Okay. Remember that this is actually with this amount of chromium, this is fully ferritic. And then we know that the nitriding response, that is a nitriding parameters which are actually a function of temperature, Rn, that is the nitriding potential and the time, right. We know that these are the three parameters. Now, to understand the way the different parameters influence, we need to keep the other things constant. In this case, temperature and the time has been kept constant. Okay. You see that it is 580 degrees Celsius and 4 hours. Okay. And now, what you see here, this A, B, C, D, these are the light optical micrographs taken from the cross section of the nitrided sample. So, what you are seeing here on the top is all these arrows indicate that is the surface of the sample. Okay, that is the sample surface and you are going as a function of the going into the sample, that is from the surface into the depth, somewhere you will have the core of the sample. Okay, somewhere here you will have the core of the sample. Now, what is the difference between A, B, C and D? As we said, we are varying only the nitriding potential. So, in this case it is nitriding potential is 0.03, 0.21, 0.54 and 0.82. The first thing is you see that the layer thickness. Okay. Let us say that what do you mean by a layer? For example, I would say that where you see the visibility of the grain boundaries until that depth, let us say that this is the nitrided layer thickness. Okay. This is the thickness, this would be about 100 and about 120 micrometer. And you see that this layer thickness is increasing with increasing nitriding potential. So, that means that by increasing the nitriding potential increase in the atmosphere implies that we are having actually the increased amount of ammonia in the gas mixture. Yeah. So, we have a ammonia hydrogen gas mixture, in that percentage of ammonia is being increased from this A, B, C and D. And now other features what we see in this micrographs is, you see that at the close to the surface you have a dark appearing region, okay, like this. Yeah, this is all the dark appearing the regions, right, and below that you have a rather very the bright appearing ferrite grains. Yeah. So, what are these differences? And as we know that as a function of time, if we look, okay, as a function of nitriding time, this top surface, okay, this region top surface of the sample is the oldest part of nitriding. Okay. Oldest part of nitriding, and the region which is at the interface with the, this is the unreacted core, okay, this is unreacted core, and this region which are appearing brighter, okay, that is these kind of regions, this is the youngest part of nitriding. Okay. So, now what it shows is that initially something actually is developing as a function of nitriding. So, that is called as a initial precipitation is, we have a so called continuous precipitation region. Yeah, this bright appearing, that is the, this is the youngest part, that is the initially, that is what develops, that is called continuous precipitation layer. And then what you see as a later developing, that is the, this is this kind of regions, the oldest part, okay, that is called as a, I call it as a later developing, that is discontinuous discontinuously coarsened region. Okay. This is called as a CP, okay, with the abbreviation, this is usually termed as a DC. Okay. You have this continuously precipitating layer developing initially, and then later some other reaction starts, that is the discontinuous coarsening, and that is what leading to this dark appearing regions after etching. Okay. Now, what is the difference between this continuous precipitation and discontinuous precipitation? So, as one can see that initially when your nitrogen is entering into the sample, what develops is a very continuous precipitation. This Cp implies sort of a homogeneous nucleation. Homogeneous nucleation of nitride phase. Okay. This is usually always known as, like for example, in this case nitride phase can be thought as chromium nitride. Okay. So, that means actually you have a homogeneous nucleation, means the rate at which the nucleation of this nitride happens is same everywhere in the material. That means it is it homogeneously develops as a very fine, okay, the precipitates are in this case would be very fine nanoscale precipitates. Okay. Now, if you look at the discontinuous coarsened regions, that is the dark appearing regions which we see close to the surface, okay, we have a coarsened chromium nitrides. Okay, so, if we look closely into these dark regions by using a high resolution microscopy like a scanning electron microscopy or a transmission electron microscopy, we would see something like a lamellar structure. Okay. If we look in a very high magnification, you see the development of like a something comparable to like a pearlitic microstructure. You have this white one is the ferrite, okay, and let us say the red one is the chromium nitrides. Okay. Like this alternate lamellae will be developing here. Okay. This is what the way the microstructure evolves if we have, for example, a chromium alloyed sample. Now, we are already seeing that these are already the coarsened chromium nitrides, right, and we will see actually what is the problem with this kind of discontinuous coarsening reaction, okay, in the next slides. Now, if we look actually how the nitrogen profile evolves, that means from the surface to inside, we want to see how the nitrogen concentration is changing as a function of depth, okay, because that is where you will know the kinetics of the process. So, what are shown in this slide is again the same iron 7 weight percent chromium. Here you have A, B, C, D, okay, and these 4 are for the different nitriding potentials, as one can see here. This is the increased nitriding potential, and then you see the development of this is the measured nitrogen concentration as a function of depth. So, this 0 depth implies this is the surface, okay. This is the surface of the sample, and then you are going into the sample, you see that the nitrogen concentration is close to about 8 atomic percent, and then that is the going down, and then you see that it is rather 0 in the core. Yeah, that is what you see that. So, this is the, if we demark here, okay, this side of the region is the unreacted region, okay, and this region on this side, this is the nitrided zone. Yeah. So, again you see that the same as what we have seen from the previous slide from the light optical micrographs, the thickness of this nitrided region, that is this depth, is also increasing with increasing nitriding potential, okay, and we will see why this is happening later, but what we see is that, so the nitriding depth, okay, is proportional to the nitriding potential. We see that there is a some sort of a proportionality between the nitriding depth and the nitriding potential. So, now we in the previous slide we seen that close to the surface you have something called, suppose for example, in any case we can divide them into also the continuously precipitated regions. This is like say DC region and the continuously precipitated region. Yeah. So, if we superimpose the microstructure, you see that close to the surface you always have discontinuously coarsened region, and you see that nitrogen concentration is not really changed from this transformation from continuous precipitation to discontinuous coarsening region. If that was the case, we would have seen some difference here, okay. But that is a situation we see in some alloying elements that I will discuss in the next slide. So, now I want to draw your attention to another feature which is shown in all these A, B, C, D pictures, okay. You see one level is indicated, okay, this line, and it is called as normal nitrogen content. What is the meaning of this? We know that, for example, in the case of 7 weight percent chromium, in case of iron and chromium being atomic weights are quite close. So, this is almost equal to also atomic percent. Okay. So, we have a, what do we expect as a level of nitrogen, okay, by under some assumptions. that is the normally expected nitrogen. So, what are the usual condition which we can think of? Initially we have a sample, this has iron and chromium in the dissolved state, okay, and it is ferritic, we know that. Now, let us say that after the nitriding we assume that complete precipitation of chromium as its nitride. So, in this case, that is for example chromium nitride CRN. Suppose these are all now the chromium nitride, for example in this case CRN, and then you have this CRN is embedded in the alpha iron, this is the ferritic matrix, that is the alpha iron. And now you can count actually what is the total amount of nitrogen associated with the CRN, that would be same as the amount of chromium, if you assume that all the chromium has precipitated out as CRN, right. So, now then the remaining alpha iron also will dissolve some amount of nitrogen, this matrix will dissolve some amount of dissolved nitrogen, this I show it also with a square bracket with the indication of alpha iron, that means it is a nitrogen which is dissolved in alpha iron. How do we know this amount? In this case we have applied some temperature, in this case 580 degrees Celsius, and for example a constant nitriding potential. So, we have seen in our first lecture that temperature and nitriding potential will set the what is the equilibrium level of nitrogen which can be dissolved in pure iron, that means a fully ferritic iron. Okay. So, that we have seen with the help of the that condition can be imposed from the thermodynamics, as if we look at the Gibbs energy, if we plot the Gibbs energy of alpha iron and as a function of nitrogen content, okay, for example Xn, and then it will be going from let us say from some concentrations, and somewhere here you have 100% nitrogen axis for example, and now you have some trend for the Gibbs energy curve. Okay. And now, if we say that this is the 100% nitrogen axis, for example here Xn equal to 1 and it is 0, this is a pure iron here and this one is here. For example, we know that we have seen that the chemical potential of nitrogen in the gas atmosphere, okay, that can be kept constant by fixing the temperature and nitriding potential. Okay. Now, if we have a T comma Rn, okay, both kept constant, that means we are fixing the chemical potential of mu n in the gas phase. Okay. Now, for the chemical equilibrium between two phases, in this case gas and the solid, so we impose that the chemical potential of nitrogen should be same, that can be read with a tangent, placing a tangent to this Gibbs energy curve, okay, with this as an intercept, as this one is constant, and wherever you see this where it makes the tangency with the Gibbs energy curve, that is the so called equilibrium. Okay. I add here equilibrium. Okay. So, this is the nitrogen quantity expected in alpha iron at equilibrium, okay, N alpha iron equilibrium. So, this can be obtained individually by doing experiments with the pure iron samples. Okay. So, how it is can be done? So, you take a very thin foil of pure iron and you start to nitride it at a constant temperature and constant nitriding potential condition, and then you keep tracking the amount of nitrogen taken up. Okay. So, that one can be done very accurately by just taking the weight of the sample as a function of time, and then the weight starts to increase and then it comes to saturation level. That implies no more nitrogen is being taken or left by the sample. That is what is the equilibrium level of nitrogen which can be taken up by the solid at the given temperature and nitriding potential. So, knowing the amount of chromium, you know the nitrogen bonded with Cr(n), and the sum of these two, okay, is called normal nitrogen level, or the content is given as nitrogen bonded with nitride particles as Cr(n), and this depends on amount of chromium, we know that amount, plus nitrogen which is dissolved in the alpha iron matrix, that is in equilibrium with the outer atmosphere. Okay. Now, you see that the observed nitrogen content, this is the measured nitrogen content, and this is the level expected under this assumptions of, like we have some kind of a situation, and this gap between the measured level, that is this gap, okay, the gap between this normal level and this level is called, this gap is called excess nitrogen. Okay. So, why this excess nitrogen comes? So, that I will now explain that. So, what we can think of the reasons for this excess nitrogen? One reason we can think of is when you form these chromium nitride precipitates, very fine precipitates in the ferrite matrix, you have this interface between the ferrite matrix and the nitride particle. Okay. All these particles have an interface with the ferrite matrix. So, the nitrogen can absorb, like nitrogen can absorb at these interfaces. Okay. And that now that can be an additional nitrogen that one can consider. Okay. So, that would be that can be written as, for example, here I am writing excess nitrogen can be due to N interface, that means it is absorbed at the ferrite matrix and nitride particle interface. Okay. That is all these locations. And then the other quantity which we can think is, we have said that the N equilibrium level of the alpha iron, that we are getting it from the experiments on pure iron. So, that will be, that matrix of pure iron will be only fully the ferrite, but in our actual samples of this kind of alloys, so when you form these nitride particles, there will be misfit strains between the particles and the matrix, because the chromium, when it is in the dissolved state in the ferrite, okay, here there is a certain volume occupied by chromium in the dissolved state, right, in alpha iron, and after the precipitation, then volume occupied by chromium in the chromium nitride, this will be different, these two are not equal. Okay. Because of this misfit, you introduce a strain fields around the particles. Okay. I will show the, so we will have a misfit strain field around the particles. Okay. These are like the ferrite matrix is strained in the immediate surroundings of the particles. Because of that strain, you change actually the Gibbs energy of your matrix, that is the ferrite peaks. This what we have shown here, this is the Gibbs energy, this is for a strain free ferrite, iron nitrogen ferrite. Now, due to the strain fields, we will change this curve, because of that your common tangent now will intersect at a different location, and that would lead to the increased level of nitrogen, that is called as a N strain. Okay. Now, these two quantities, okay, can actually contribute as a excess nitrogen, and this N interface, that depends on the amount of the volume fraction of nitrides and the size of the nitrides, right. So, that would decide actually the overall interfacial area, and that would also dictate the, that is why the amount of nitrogen. So, how to obtain quantitatively, because what you can measure from this kind of measurement is the total nitrogen, and here we are talking about 4 types of nitrogen which we can think of should be present, and this total amount, right. This in the total amount, all these quantities can be present, and this can be extractable, all these quantitatively, from the so called nitrogen absorption isotherms. Okay. So, I will not be discussing that in this lecture. And now, if we move on to the same thing with, now we are showing the iron chromium. If you look for example, iron vanadium now, okay, we are now switching to a different element, that is iron vanadium. Again the temperature and the time and the nitriding potential applied in these samples is this shown here, and what you see here as this A, that is the light optical micrograph, the cross sectional micrograph. Similar to iron chromium, you also see that there is a continuous, this is the CP region, and a discontinuously coarsened region, DC region close to the surface, and you have a unnitrided or unreacted core, that is here. You see that you will be able to distinguish these regions. Yeah, you see that when you do the etching with nitol, this unnitrided core as not in that region, we are unable to reveal the ferrite matrix grain boundaries, whereas in the nitrided region we are able to reveal that. That is because in this unreacted core, vanadium is present in dissolved state, vanadium is in dissolved state. So, that will actually modify the way the your etching reaction happens, whereas here your vanadium is precipitated out. Okay. In this nitrided region, vanadium is precipitated, vanadium has become vanadium nitride for example, that is where actually its etching reaction is different, that allows nicely distinguishing these regions. Okay. Now, if you look at this picture B, okay, this is below this night micrograph, is the what is the level of hardness as a function of distance away from the center of the sample. Okay. For example, this is the surface of the sample and you are going into the center, you can interpret like that, or this is the center of the sample, I can go to the positive side or negative side to reach the surface. So, you see that the surface hardness, okay, this is this region or this region, because this sample has the because it is a thin plate having the 2 surfaces, right. So, if you have a cross section like that, this microstructure is having a, this is the center plane, and here you have a DC region as well as on this side, okay, both sides you have a discontinuously coarsened region, and below that you have a continuously precipitated region. And important point to note here is this discontinuous regions, okay, the DC less harder than Cp. Okay. The discontinuously coarsened region shows less hardness than Cp. You see that here this continuous precipitated region has about 1200 HV. Okay. This is the level of hardness in this region, okay, that is this region, and close to the surface where we have a discontinuous coarsening, there is a drastic drop in the hardness level. Okay. You see that there is a drastic drop in the hardness level. So, that is what actually shows that we have already known that in this region already there is a coarsening of the precipitates, right, discontinuous coarsening. So, because of coarsening of the precipitates, their precipitation hardening effect has reduced. So, that is leading to the decreased hardness, okay, that is understandable in that way. Okay. So, now if we move on to the comparison with the the similar situation like in iron chromium. Now, in this case it is iron 2 weight percent vanadium, again these are the nitriding conditions. What you see is also there is a so called excess nitrogen, okay. This is the normal nitrogen level and this is the excess nitrogen level, and we will do some in the tutorials how to calculate normal nitrogen content and the all those things. And what you see here is these are all the hardness indents, okay, which are quite small, okay, as compared to these ones, okay. this is larger the size, that means it is a less order. This is the core of the sample, okay. This is the core and this is the nitrided region. As we have seen in the previous slide, with 4 weight percent vanadium under the same nitriding conditions, you see that 580 degree Celsius 10 hours and Rn of 0.1, we have seen this appearance of this discontinuously coarsened regions, right. That is where we have a lesser hardness, okay. This is not the case for the same conditions when you have only 2 weight percent vanadium, okay. You see that there is no discontinuously coarsened regions visible at the surface. This is the surface and you are going into the sample and you see only continuously precipitated region. That means Cp to Dc transformation has dependence on amount of vanadium or chromium, for example. Yeah. So, that is the situation. As we have seen in the previous slide, because the discontinuous coarsening decreases the hardness drastically. So, we would like to avoid this discontinuously coarsened region coming at the surface, because our whole intention is to get highest hardness to the surface, right. So, that is where actually, so it is important to optimize the chemistry and the conditions such that we will have the highest hardness at the surface. There is one difference between iron chromium and iron vanadium. In both the cases, depending on the amount of chromium or vanadium, you have a discontinuously coarsened regions, that as these are dark appearing regions. But if you look at in the case of iron chromium, the nitrogen content is same in the DC and Cp regions, okay. N content is same for DC and Cp. But here in this case of iron vanadium, if you look here in the composition profiles, you look at this is the nitrogen concentration as a function of depth. You see that this is the discontinuously coarsened region, okay, close to the surface, that is this region, okay. This is the same as this here, and you see that there is a decreased level of nitrogen, okay. So, in both the cases you see decreased hardness, but in case of iron vanadium you see also the decreased level of nitrogen, and that can be due to the capacity for excess nitrogen somehow reduced here after discontinuous coarsening, because we see that it is still above the normal level. This is the normally expected level, and after discontinuous coarsening, of course, it is lesser as compared to in a continuous precipitation region, that is here, okay. This entire region is continuous precipitation, but it is still higher, that means excess nitrogen capacity has reduced here, okay. And that can be understood based on the coarsening of the precipitates, okay. When you have a precipitate coarsening, we will reduce actually the overall precipitate matrix interfacial area, and that will reduce the amount of nitrogen which can be taken up, okay. Now, in the overview lecture, we have also said that thermochemical surface engineering treatments have to be tuned not only to get the highest hardness to the surface, but also to get a desirable residual stress state. It is often we need compressive residual stress states. So, now if you see for the in this picture what is shown here is, this is the light optical micrograph, okay, of iron 4 weight percent chromium with the nitriding conditions, and this is the white dashed line is the surface of the sample, and you have this DC region, that is the zone 1, okay. This is the DC region, and the zone 2 is Cp region. And now, if we look at what is shown here in this side is the residual stress level at different depths below the sample, okay. If you look actually the residual stress, if we start to measure as a function of depth, that can be done with a a diffraction technique, which I will not go into the details. Then you see that in the zone 1, that is actually the DC, and this is the CP, and this is the unreacted core. You see that the stress level is more or less 0 in the core, and what you see is that in the DC region you have the compressive the tensile residual stress. You see that this is the surface of the sample, right, and here you have generated now the tensile residual stress, and the CP region as a compressive residual stress. You see that now by this this DC reaction, okay, development of this the discontinuously coarsened regions not only reduces the hardness, but also introduces the tensile residual stresses, which are not at all favorable for a good fatigue resistance, right, because all the cracks start to initiate and travel into the sample from the surface. So, we always would like to have compressive stresses at the surface. Okay. So, that way this is also very important to keep in mind that it is not only the hardness level what we are trying to optimize, also the residual stress level also needs to be optimized simultaneously. Now, what we have seen is about the situations in which this chromium and vanadium, where the element actually is precipitating quite quickly, okay, and you are forming actually a sort of a layers, right, of a nitrided region is growing like a layer. But now you have a different type of elements. For example, here I will be picking up this iron silicon. Okay. So, if you add a silicon into the steel and then if you start to nitride, what happens? Okay. Now, I am showing these things because in the, if you remember in the previous lectures, we have seen that chromium and vanadium show some character, comparable character with respect to the way iron nitrides tries to grow, and the silicon and aluminum have shown a very different pattern. Now, the same situations, same kind of contrast we are able to see also in the, when we try to do the nitriding in the ferritic condition. So, what you should see here is you have this A, B, C, D, E, and these are the light optical micrographs after the for this iron silicon samples. This is a unnitrided sample, just as a reference, the microstructure. Okay, you have a recrystallized microstructure. Then this is after 30 hours of nitriding, this is after 65 hours, this is after 165 hours, and this is after 332 hours. What you see is, like in case of iron, chromium and vanadium, here you are not seeing any distinguishable regions as a function of depth, the where there is etching contrast and you see grain boundaries and you do not see grain boundaries, something like that. You see more or less homogeneous etching contrast. You see that here there is a change in the etching phenomena, but that looks similar throughout the depth, and that is what you see also with increased time. Yeah. So, that implies that there is something happening, but that is happening quite homogeneously. If you look in more detailedly the scanning electron microscopy, what are shown here A, B, C, D are the scanning electron micrographs. You see that after 30 hours you have some small precipitations are developing with something happening along the ferrite matrix grain boundary, and with increased time to 165 hours you see that now they start to develop more, and after 332 hours you have more density, and this is a higher magnification picture of the 332 hours, you see also something developing along grain boundaries. And this kind of observations were not there for iron, chromium and vanadium, and here you see that a distinguishable the precipitates growing, right. So, if you look the hardness, how the hardness is changing. If you remember from the iron, chromium and vanadium, there is a significantly high hardness to the nitrided region and a sudden drop into the core of the sample. But here what you see is, this is the hardness level as a function of depth in the sample. The level of hardness, okay, is quite same throughout the thickness of the sample. Okay. That means it is something like a bucket filling kind of effect, and also the level of hardness, if you see, it is only a marginal increase as compared to a the nitrided, this is the base level hardness, as compared to that you have only a small increase in the hardness. That is understandable because we have seen in the previous slide the precipitates are coarser, right, because they are that is already tells that why they are coarser, because reaction is progressing very slowly. You look at these nitriding times, okay, they are way orders of magnitude higher in nitriding times than in case of iron, chromium or vanadium. Okay. So, the same kind of results you can see also if you look at the concentration of nitrogen as a function of depth. This is after 165 hours. You are see if you look at this blue, this thing as a nitrogen concentration, that is more or less homogeneous. There is a scatter, that it is a we should not worry about it, because you have a coarser particles of nitride in the matrix. Now, it is possible that when you are probing when your electron probe hits the more of the particle, then you see the nitride particle, there can be a increased peak in the nitrogen content, and that is what you see, that even after more time you see that this level. Now, if you look at this is the average level that has gone up here, but homogeneously. If you look closely as this analogy, if this is the nitride particle, then if there is a more nitrogen, then we should also see more silicon. That is what you see here, when there is a the peak in the nitrogen content, you also see peak in the silicon content. So, in this case you are forming silicon nitride precipitates, but the kinetics are extremely slow. Okay. So, that is what we can see from this. So, now with this I would like to summarize this lecture. We have seen that depending on the type of element, for example, the chromium and vanadium kind of elements, which we can we have classified them earlier in the lecture as strong nitride formers. I mean, they try to interact very quickly with nitrogen and leading to a significant increase in the hardness, and the hardness depth profile will be rather sharp. You have a hardened region and a unreacted core which is soft, that is usually desirable for the applications. Whereas, you have other class of elements, for example, here we have discussed about silicon, and the same holds with also sort of for aluminum. You see that the precipitation is rather slow, and this actually leads to very slow kinetics and a much smaller hardness because of larger size of the precipitates which evolve. So, thank you. With this I am at the end of this presentation, and we will meet for the next lecture with a discussion on how we can interpret the kinetics of nitriding from the growth from the way the layers are growing. Thank you.